Okay. Alright, so we have in case of VSB-SC, we have already seen the input output filtering characteristics and their relationship, right. So let us just assume one particular filter. So we have already seen this relationship, HOF is 1 by HIF plus FC plus HIF minus FC, right. This is something we have seen, okay. But also remember, this particular criteria is required only when I am within my band, because what I was doing, I was trying to detect my signal which is MF, which is valid up to B. So this filter characteristics must be valid up to B. After that, whatever happens, I am not bothered, as long as it is a low pass and it is rejecting that higher frequency term. So as long as this is happening, I know that things will be all fine, okay. So because I have to only concentrate on that band, rest of the portion are not that important, okay, because anyway nothing will be there, okay. So that is what we are trying to see. Now if we just employ this method, that within this band, this HOF is a very simple filter, it is a simple low pass filter, okay, ideal low pass filter. Let us think about that. So I can say that HOF must be 1 within this band, okay. For low pass filter it must be flat, otherwise the signal will be distorted, my MF will be distorted, right. So HOF must have unity gain within that band of interest. Outside that band it might be anything, so I am not that much bothered, only thing is that it must be having a low pass characteristic. So it might be something like this, or it might be also something where the roll off is there. So within the band, as long as it is unity, I have no problem. So that must be ensured, rest of the things are not that much important to me, okay, because it is all defined within that band only. My actual signal was within that band, so all I have to do is within that band it should be all right, okay. All the other places what is happening, it is not very important, but one thing you need to keep in mind, that it should not be spreaded in such a way that that 2FC term is coming back. So it must be having that low pass characteristics and it is not taking that very high frequency term, which we have rejected while doing this calculation, right. That relationship we have got by saying that these two terms we can actually cancel. So it should not be taking these two terms. So whatever it is, it must be satisfying that criteria. As long as it is doing that, I have no problem, okay. So if I assume this, so within the band I can write that immediately HIF plus FC plus HIF minus FC, that must be 1. So this happens to be one of the desired criteria of designing my input filter, okay. Output filter now is becoming very simple, it is just a low pass filter. As long as it is flat within that band of interest, it is all right. So if I just take that, then I can see that input filter has to be properly designed. Whatever it is, it must satisfy this thing. So let us try to see first what is this input filter, means how that should look like, okay. So what we are saying, that this input filter is a band pass filter, right. So suppose I have a Vsb-SC modulated signal, okay. Now I want to put an input filter. So what do? I put an input filter which has a characteristic something like this, okay, and again it should be symmetric because it is a real circuit. Suppose I have a characteristic like this. Now here I can see the slope is not very sharp and it will of course distort the signal. But what will happen, let us say this is FC and this is minus FC. Now you shift, you put this thing, this criteria, right. Let us say this is half and this is also half. or I should not say half, let us say this is 1. Okay. So, what will happen? Now, I have to shift this to, so all I have to do is this h, whatever h I have to shift it to plus Fc and shift it to minus Fc and add these two, and then I have to see whether it is giving me 1. Then only I can say that this is a valid filter for me. Okay. The way I have adjusted it, so this frequency and this frequency will be all similar, right. So, if this is Fc plus some delta, this must be also delta. If this is also delta, this must be also delta. Okay. So, these things has to be all properly fixed. Okay. So, if this is the case, now shift it by Fc. So, what will happen? This will be completely shifted by Fc, and you shift on the other side by Fc. So, they will actually slope should be all same, they will actually overlap like this, that is the 0, these are deltas. Now, because it is a constant slope, if you add these two, they will all give 1. So, if you just add these two things, they will just give 1, so it becomes flat, and you can now see from minus b to plus b, it remains flat. So, that means this criteria is being fulfilled if I design my filter this way, right. So, there now you can see that whatever relationship that we have got over here, I can actually have a realistic filter, okay, where there might be some roll off, okay. Of course, it needs to be linear, or maybe some near linear part I can just select, and that will still suffice, okay. So, I'll be suffering, probably the filter will have some this thing. So, that will create little bit of distortion, but as long as this slope is almost tracking whatever I wish to do, it will almost give me similar result. Okay. So, if I can do that, I can immediately see that if I put that HIF plus Fc and HIF minus Fc, I can always get back whatever relation I have, means to get my actual SSB signal back. So, from the VSB signal, actual signal back, whatever criteria I have put, I can actually employ that. So, now I have seen that there is a realistic filter realization that can be employed over here, and which can still give me, due to the filter designing, still give me back my signal back. Okay. So, once we have done that, let us try to see whether Vsb-SC signal also has similar representation as SSB signal. That will be our next target. Okay. So, for that, what we will try to see, that we will assume that maybe that is the case. Okay. So, we will say Vsb t is nothing but some mt cos omega ct, which is almost similar to a SSB signal, and some mvt sin omega ct. Okay. So, we are just trying to prove that there is a representation like this. Okay. So, we are just, it is almost like we are assuming this, and then try to see whether we get something which are not contradictory. Okay. So, that is what we are targeting. So, we are assuming that okay, there is a representation which is like this, where this mvt is nothing but my message signal passed through a filter, okay. Or I can write mvf, this is actually my mf followed by a filter called ff, okay. That is the filter transfer function. Okay. So, some filter I will be requiring, through which if I pass this mf, and of course, we will later on see that this ff must have a low pass characteristics. Okay. So, it is a filter which I am aiming, I still do not know, I will be proving what this filter is. So, which gives me this MVT. So far we are just assuming, okay, that this MVT can be represented as this, almost similar to our SSB. In SSB what was happening, the signal was passed through a Hilbert transform. So, Hilbert transform has a transfer function like this filter, and we are just passing it through it. The same thing we are doing, because we have said that we want a representation almost similar like SSB. That is what we are doing. Okay. So, immediately what we can write, this phi VSB-F, we can now represent it in frequency domain, right. So, if MVF is written as this, I can now write this as MF plus FC plus MF minus FC, of course because it is cos omega ct, so divided by 2, plus because it is sine, so it should be 1 by 2j, and I will have this MV F minus FC minus MV F plus FC, right. I will have this. Now, MV I can write as MF and FF, I can write that, I can take these two in the same part. So, I will get finally MF minus FC, if I just take F minus FC, there will be a half term, and I will have 1 minus J F F minus FC, if you just do a algebraic ordering. And similarly, if I just do M F plus FC, I will get again another half 1 plus J F F plus FC, I will get this, right. So, this is what we are getting. So, what is happening now, this MF minus FC and MF plus FC, see this is my VSB-F. What was my earlier assumption? It must be MF minus FC plus MF plus FC into HIF, that was my earlier assumption, okay, or I should not say assumption, that was the actual generation. So, this must be similar to that. If that has to be the case, then this and this both should be HIF, right. So, this should be HIF and this should be also HIF. So, let us try to put that, okay, that okay, if this has to be equal, then this should be, both of them should be equal to HIF. If I put that, do I get a contradictory result or do I get something which is what we have proven already? So, if I just say HIF is half 1 minus J F F minus FC, right. So, from here I can calculate HI F plus FC, right, which is nothing but half 1 minus J, that should be FF, right. And from the other relationship I can get HIF should be half 1 plus J F F plus FC. From here I can get HIF minus FC, okay. So, immediately that will be half 1 plus J F F. Now, what was my relationship? HIF plus FC and HIF minus FC. If I add these two, that must be 1. Add these two, you can immediately see this will get cancelled and I will get half plus half, that is 1. So, it is not giving any contradictory result, okay. So, the filter that I have designed, it is actually being consistent with that. So, therefore, I can say my filter F is having this relationship, okay. So, it is just that filter, if I just pass my signal through this filter, I will be getting the representation which is already being proven for SSB-SC. I get almost similar representation for VSB-SC. So, that is why I can also see, now things are all consistent. I can also see if I just multiply this by a 2 cos omega ct, immediately I get my signal back, because I multiplied by 2 cos omega ct, put a low pass filter, I will get my MT back. That is consistent. Earlier also we have proposed the same thing. So, we can see that with this particular thing we will be always getting back this thing, right. So, basically I can now put my modulator as this. So, I will be having MT, sorry, the means for the modulation, what I can do, that MT I can multiply by a cos first. So, let us say 2 cos omega CT followed by HIF, the filter I have designed. So, the demodulator will be take this one, multiply with, because we have now seen that it is represented as this, right, it is represented as this. So, if I just multiply by cos and followed by a low pass filter, I should be getting, so multiply by 2 cos omega CT followed by whatever that HOF, which is a low pass filter, I get my MT back. Okay. So, this is actually the VSB-SC modulation and demodulation. It is pretty simple, that only thing is that this filter has to be carefully designed, the way we have demonstrated in the earlier case. So, that has to be very carefully designed, so that HIF plus FC and HIF minus FC gives me 1 in all the places. Only thing is that beyond that it is not that much required. So, whenever you are designing that filter, you can always say that I need to have this, after that it can have any roll off. Okay. So, let us say this is my FC, this is B, up to B I means FC plus B, okay. And let us say this is my FC minus FC minus FC minus B, after that it might have any roll off, that is not a problem, because if you just do F plus, so this is the spectrum, if I just do HIF plus FC and F minus FC, what will happen? These two will add up to 1, so up to B and minus B it will be flat, after that it will have this and this roll off, okay. So, no problem in that, that can be anything. Only thing is that I have to ensure that whatever that filter, that is flat up to B, beyond that what I put, it is not a problem, okay. So, that is how generally VSB signals are being generated. So, basically you have to, all you have to do is you have to employ this filter and you have to characterize this roll off properly, whatever roll off you wish to do. Now, regarding the roll off, it depends on what kind of circuit you can choose, and accordingly there will be a trade off of how much bandwidth you take. Suppose you want to have a little lesser roll off, okay, then the filter characterization accordingly will be simpler, because you do not need to go for very higher order filter. So, what will happen? It will take some extra band. If you start going towards higher and higher order filter, the roll off will be sharper and you will be saving more and more bandwidth. And you can see that at the end, when you can make this roll off almost sudden, then it goes back to SSB. So, VSB is nothing but from DSB slowly you can move up to SSB, and it all depends on what kind of roll off you wish to give to your filter, okay. So, depending on that your filter designing will be more challenging or less challenging, but whenever you have more challenging filter design, you will be saving on bandwidth. Whenever you have a less challenging filter design, probably you will not be saving bandwidth that much, okay. So, in TV spectrum, probably they go up to the 50% of this band, okay. So, they take overall band, if it is 2B, they take 75% of that. So, that is what they do, they save 25% of spectrum, okay. And also they put carrier, you will see that why that carrier has to be put, that we will discuss later on. Whenever we talk about carrier recovery, we will be discussing more about that carrier recovery, means why carrier has to be put in SSB signal, okay. So, after this, now we have discussed about two bandwidth efficient scheme, one is VSB-SC, one is DSB-SC, one is SSB-SC, right. Now, we will discuss another bandwidth efficient scheme which is called QAM, quadrature amplitude modulation. So, what is this? This is something like that. Let us say I wish to generate QAM. So, what I do actually, instead of modulating one signal, now I take two message signal. One is M1T and the other one is M2T. It is almost like multiplexing. I am taking this to message signal, and within the band of 2B I wish to transmit both of them, as long as both of them are actually demonstrating similar band. So, they are similar signal. They might be having different spectra, different time domain representation, but the overall band that is being considered for them are similar. As long as that is happening, I can actually represent them as this composite signal. So, it should be M1T cos omega Ct plus M2T sin omega Ct. So, that is exactly what we are trying to achieve. Okay. So, through this modulation. So, in QAM what we are targeting is, we wish to basically transmit two signals simultaneously. Okay. If you just try to see the spectrum that it will be occupying. So, if I multiply by cos omega Ct, it will still have similar spectrum shift. Okay. It will still be occupying that Fc plus B to Fc minus B and in the negative half. And if M2T is also having B bandwidth, if I multiply by sin, it will also be occupying same band. Okay. So, both of them will occupy a similar band and they will superimpose, but just we have to see, because the way we are producing them, we are multiplexing them in the same band. So, they are getting superimposed. Is there a possibility that we can separate them out? That is what we will have to appreciate. Can we separate them out after this? So, modulation was fine. I know that they occupy, if they are having similar baseband representation, they will be occupying similar band, but can I really demodulate them and separate them out? That is something which we will be discussing now. So, what we have to do is, suppose I want to demodulate back M1T, that is my target. So, what I do, I take this QAM signal, okay, quadrature amplitude modulated signal, phi QAM, put a band pass filter around Fc of 2B. So, I will be getting the entire this composite signal. Okay. I will now multiply this with 2 cos omega Ct. Okay. So, I will just multiply with cosinusoidal. So, what do I get? So, this is, I am calling this as x1t. Okay. So, what do I get? Now, this will be multiplied by cos, so that should be cos square. So, I will have 1 m1t plus cos 2 omega Ct. So, m1t into cos 2 omega Ct, and this will be 2 sin omega Ct cos omega Ct. So, that should be m2t sin 2 omega Ct. Right. Now, a very nice thing has happened. Both of these things has gone to a higher frequency. Only thing that is left, which is at the baseband, is M1T. I put a band pass filter, I get this signal back. So, basically I have an option of demodulating only M1T from this. Similarly, if I just multiply this by sin, you will see that I have an option of demodulating M2T back. So, if I produce x2t, which is phi QAM, of course that should be t, into 2 sin omega Ct. Now, what will happen? This is, the first term is now becoming m1t sin 2 omega Ct, and then it should be m2t into 2 sin square, that is actually cos 2 omega Ct minus 1. Or 1 minus, right. So, 1 minus this, right. So, what I get, again this term, it is a modulated signal, again going at 2 omega Ct. So, I can neglect this into this, that can be neglected as well. So, I get back M2T after I do a band pass filtering. So, basically I have now option of demodulating both the signals, okay, simultaneously, but the good part is both of them are occupying B band. So, it is actually 2B band. So, within 2B band I am able to transmit 2 such signal. It is almost similar means bandwidth efficient as SSB signal, because in SSB also if I had this 2B band, I was putting 2 SSB signal, whereas here I am probably occupying a composite signal and it is having both of them, right. So, M1T as well as M2T, and I now know that I can actually demodulate back both of them. So, equivalently I am able to transmit almost similar, means similar bandwidth efficient modulated signal as SSB. So, what will be the corresponding modulator and demodulator? So, I just have to generate a local cos omega ct, right, multiply that with our message signal which is M1T, and then from cos I have to produce sine. So, put a pi by 2 phase shift, multiply with another signal M2T, right. So, whatever you get, you add them together and put it in the channel, right. So, that is the phi QAM T. Once you receive that, you put in 2 arm, and then again locally you generate 2 cos omega ct, you directly multiply and then followed by a low pass filter, you will be getting M1T back. If you just give a pi by 2 phase shift, so this will become sine, multiply and then followed by a low pass filter, you will be getting M2T. So, that is actually the x1, sorry, that is the x1T and this is the x2T just after or before the modulation, right. So, this is what which will be happening if I do a demodulation, right. So, modulation demodulation is pretty simple, right. Now, can we now say that this is probably the best modulation scheme, QAM? Right now we cannot give that answer, but bandwidth efficient wise probably yes, it is equivalent to DSB, and we can say that the transmitter part is not as hard as, sorry, bandwidth efficient wise it is equivalent to SSB, but transmission part is not as hard as SSB, because we do not have to employ any filtering like our SSB. Okay. So, either be it Weber circuit or any other way, we do not have to do that. Okay. No Hilbert transform is involved in this, right. So, that is also a good part, and we are able to modulate similar things. But later on you will see that if this, there is a carrier recovery process, because I am doing this demodulation coherently, right. We are there is non-coherent and coherent demodulation. Probably I have not talked about these terms, but I have been keep on mentioning about it. So, non-coherent is like that envelope detector. That means I do not need a local carrier, I do not have to generate local carrier which is in synchronous in phase and frequency to the incoming carrier, I do not have to do that. So, that is called non-coherent. That means the receiver part is pretty simple and I am not having any influence on carrier generation. Okay. Whereas coherent is, means I am subject to, my receiver performance will be subject to how good I am in generating the local carrier at the receiver. Something is coming already with carrier because it is modulated. So, that same carrier I have to somehow extract, so that the phase and frequency are completely asynchronous with the incoming carrier, and then with that local oscillator which is generating synchronous phase and frequency carrier, I have to demodulate it. Okay. So, whatever we have seen so far, amplitude modulation was probably the non-coherent, means there I can employ non-coherent demodulation. Vsbsc definitely requires a coherent demodulation, because I have to multiply by carrier. SSB also, if I do not put carrier, it requires a coherent demodulation. and for VSB also we have seen that it requires a coherent demodulation. This one definitely I can see already that it requires a coherent demodulation. Okay. So, this coherent demodulation, if I have, there are all possibility that whatever carrier I will be generating, that might have some phase drift or frequency drift compared to the incoming carrier. And now what we will try to do, we will try to look into that part. If there are drift, what happens to all this coherent demodulation part. Okay. So, if there are some drift in frequency or phase, how I will be suffering, what kind of suffering I will get. For DSB, what kind of suffering I will get, for quadrature amplitude modulation, what kind of suffering I will get. SSB and DSB, similar things will be happening. Okay. But specifically I will be targeting these two, and there you will see probably this is not as good as Vsbsc. Okay. Both of them will have detrimental effect, but probably this one will have more detrimental effect. And we will also be able to prove that whoever is bandwidth efficient like SSB or VSB will be also able to prove that carrier recovery is almost impossible over there. Okay. Similar thing over here also. So, carrier recovery will be impossible, that is the first thing. Second thing is, even if we somehow get the carrier, if you wish to demodulate, if you have some phase or frequency offset, you will be having a detrimental effect over it. So, in the next class probably we will be discussing that part in detail. Thank you.